Hello, I'm David Greenwood from Newcastle University in the UK, and I'm presenting poster 385, which is Flexibility Scheduling for Distribution Systems, a case study in Austria. This work was led by my colleague Da Huo, and it's part of the H2020 Merlon project, which is looking at island local energy systems and how we can use them to improve reliability and unlock new business models for flexible demand providers and get the best yield out of renewable energy generation. And this paper is about how we schedule flexible assets within the distribution system to deliver the best value for all the customers who are connected there and maximize the amount of renewable energy that we can use. Okay, so there are some challenges in the system we're looking at. So I should say there are two pilot sites in this project, one in Austria and one in Spain. This is the Austrian Güssing pilot site that we're focusing on for this paper. So there are some challenges in this distribution system. So the first one is that the area we're looking at is an area called Strem, which is a 6-bus part of the wider network. This is in the east of Austria, and it has very large penetrations of renewable energy. So the renewable generation is typically much greater than the demand within this network. And then the other problem we have, and those renewable generators are all growing. The other problem we have is that the voltage limits are very strict for this network. So in Austria, there's a voltage limit of plus or minus 2% of the nominal value, which is much more stringent than other countries. And the combination of these two factors means that we've got kind of imminent constraints on the network, and the problems that we might have there are having to basically waste some of the renewable energy that we're generating on this system. So what are we doing in this paper that I'm presenting today? So we're looking at a day-ahead scheduling scheme, which takes a forecast of what the demand and the renewable generation are going to be, and those are generated using a method that's presented here at the conference in paper 454. And it takes also estimates of how much flexibility there will be available at each node in the network. It then uses convexification techniques to make the power flow equations, which are non-convex and non-linear, into a convex approximation of themselves, which makes that we can solve them much more efficiently and actually with full accuracy if the network is radial, which it is in this case. And what we're trying to do is manage our constraints at minimum cost. We're handling uncertainty, so the uncertainty comes out of the forecast model. So from doing analysis on our forecast, we can look at what the kind of distribution of the uncertainty is, and then we can put that into the scheduling method here. So we're using what's called a 2-point estimate to handle uncertainty, and then we're able to schedule the flexible resources. So basically for each half hour or 15-minute period, we can tell each flexible asset and a battery storage system what to do. So are you going to use more energy, use less energy? If you're the battery, you're going to absorb energy, are you going to inject energy? And the idea is that we formulate this as an optimization problem. So we take demand generation, the price of energy in the wider system, the constraints of the network. We use this to form an objective, which is to basically minimize the cost of meeting the demand for all the customers over the full 24-hour period. We have constraints, which are the limits of the different networks assets, so including that plus or minus 2% voltage limit, and the constraints of the battery system we have, so we can't over or undercharge it. And this gives us a kind of quite complicated optimization problem, but one that we're able to solve very efficiently. And then that gives us a schedule which is then sent effectively out to all the different flexibility providers, and then they follow those instructions throughout the day. There is also a provision that if we have an imbalance in the system, so what that means is the demand or the generation are no longer following their forecast correctly or close enough for us to be considering the decisions we've made in the scheduling system to be optimal, then we rerun the whole process and re-optimize it based on new information. So in the bottom middle, you can see just a diagram of the system. You can see where we've got flexible customers and the battery system and other flexible demand. And on the right-hand side, you can see some examples of how we schedule. So the top two figures are just what the battery energy storage system is doing. So here on the top figure, you can see the amount of energy and the price of electricity. And what we see is that the battery fills itself up when the energy is cheaper, and then discharges during the higher price periods. And that means that the customers are getting energy which has been effectively generated by the renewable sources during the cheap periods of the day and using that in the evening where it would be more expensive. And then on the bottom right, we can see the management of network constraints. And essentially what we can see here is that all of the voltages are within that range of plus or minus 2%. And if we hadn't scheduled the system in the way we have, they wouldn't be. You might notice that they're very far within it, and that's because this is accounting for uncertainty in the different forecasts that we've got. So this is confident that even if those forecasts are wrong, by a certain degree that's accounted for in the 2-point estimate, that we will still be within the limits of the system. Okay, so I hope you found this interesting. If you, as I say, there was another poster which is number 454, which you can go and look at if you want to know about the forecast which provides the input to this scheduling system.